Yeah, good morning, everybody. So we have been discussing about the forward converter. So in the last class, we discussed about the forward converter operation. What are the three different modes of operation? And then, so what is their operation? Then waveforms that we discussed, and the equations of the inductor current for both on time and off time. And then we discussed about the inductor current minimum and maximum currents. And then we discussed about the reflected secondary currents and also reflected primary currents and also voltage across the inductor and also maximum peak current that we discussed. Okay. So now today we are going to discuss a problem here. This problem is given that a current rating of a medium forward converter is given. A single switch forward converter is designed with a practical input voltage of 200 volts and output voltage of 12 volts and the power rating of 18 watts, and the switching frequency is 100 kilohertz. Magnetizing inductance is 2 millihenries. So in this one, we have to find out what is the output peak current ripple. So the resistance is 10% of it is okay, and determine various currents. Okay. So and also is given that the unity turns ratio between the primary and tertiary winding and maximum duty cycle is 50%. As we mentioned in the last class, also while we're discussing, the duty cycle is limited to 50% because of the tertiary winding. And all the losses and device voltage drops and effects, the effect of leakage can be neglected. Okay. Now, in this one, we have a problem is that. So what is the formula for this output? What is that? Ripple current formula. So output ripple current formula. So we had a formula in the last class. Delta IL naught peak to peak is equal to so Ri into I naught. Okay. So Ri is given in the problem and I naught also we have to given. Okay. Is that what is this output inductor value mentioned, right? Output inductor value. So L naught value is V naught into 1 minus D times of switching frequency into delta IL naught peak to peak. That is a formula for the first problem what is asked. Okay. And secondly is asked to determine the various component currents. Okay. So we have discussed about the different currents we have, right? What is the different currents are IL naught minimum, IL naught maximum, and IL naught RMS currents. And we in the second we have a diode is there, a diode D2 current, diode D2 current. So like in RMS and diode D2, what is the D average current? So similarly, diode D1 also there, right? ID1 currents like RMS and ID2 average DC currents. Okay. And all this, and also we have a magnetizing current. Yes, magnetizing current, peak current also there. And we also different reflected secondary currents, that is IS minimum dash. Okay. And reflected maximum current, IS maximum dash, all this will be there. And we have called as primary currents. Okay, these are secondary, right? So similarly, what is primary reflected current IP minimum, that is equal to IS minimum dash. Okay, and we also have IP max. So what is the current average and RMS currents of switch current flowing to the switch, right? We have a switch in that. Okay, and we also have also have a tertiary winding, right? Primary winding or secondary winding and also tertiary winding. So all this we have to discuss. Okay. In the first problem, so we have to find out the inductance value. In the second problem, we mentioned only different various currents. IL minimum, IL maximum, IL RMS, current flowing to D2, current flowing to D1, maximum peak current, of the magnetizing peak current and secondary reflector currents, primary reflector currents, and current flowing through the switch and current flowing through the radiator vent. All these we have to discuss here. Okay. So right, I'm going to start the one by one here. So here, what is he mentioned that duty cycle is 50%. So duty cycle he mentioned is 50%, and the minimum input voltage is 200 volts. That is mentioned here. Okay, and max output voltage input voltage is given as 200 and output voltage 12. Okay, so can we find out the turns ratio here? Turns ratio N is equal to output by D times of input. So in the last class we discussed, while we're discussing here, 1 by N times of V output by V input. So from this you can able to get this expression. So 12 divided by 0.5 into 200. So it would be 0.12. Transformation ratio is 0.12. Next, what is the output current? Output DC current. So here in this one, they given a clue is that power output P is equal to how much watts is given? 180 watts, right? And that is equal to V naught into I naught. So from this, I naught is equal to P naught by we take P naught by V naught. So 180 by 12. So it would be 15 amperes. Okay. Next, peak to peak. Peak to peak output inductor ripple current. Output inductor ripple current. So what is the formula? Just now I told you delta IL naught peak to peak. So which is equal to Ri into I naught. So the problem is given that Ri is how much percentages? I hope it is 10%, right? 10% means 0.1 into 15, that is equal to 1.5. Okay. Now this is 1.5 amperes. Now the output inductance. Finally, first question answer. Output inductance that is equal to L naught, and that is V naught into 1 minus D times switching frequency into delta IL naught peak to peak. Okay. Now substitute all these values. Output value voltage given is 12. 1 minus D is given is 0.5. Divided by switching frequency is 100 kilohertz. 100 into 10 power 3 into delta I naught IL naught, which we got is 1.5. So from this we are going to get after solving this 40 microhenries. So this is the first answer, that is 40 microhenries. Okay. Answer for the first question. Answer here, this is L naught. Okay. Next question is mentioned that different currents here. Okay. Second question is different currents. Various currents we mentioned. Various currents. As we discussed here, there are many currents. Okay. So in that one first here, minimum and maximum secondary currents. Minimum and maximum secondary currents. So I will call this minimum IS minimum because secondary. That is equal to IL naught current flowing through the inductor. That is IL naught minimum. That is equal to formula which we discussed already. I naught into delta IL naught peak to peak divided by 2. So I naught which we got is 15 and IL naught is 1.5 divided by 2, that is 14.25 amperes. And similarly, if you find out IS maximum is equal to IL naught maximum, that is equal to I naught plus delta IL naught peak to peak divided by 2. So this is 15 plus 1.5 divided by 2, that is equal to 15.75 amperes. Okay, so these are the secondary minimum and maximum. Now, what is the RMS currents in the inductor? RMS current in inductor. So IL naught RMS. Okay, that is equal to. So this is a formula. We have to take a mode of this. I naught square plus delta IL naught peak to peak square divided by 3. Okay, so this would be 15 square plus 1.5 square divided by 12 square under root. This is 15.01 amperes. Okay. So next question is what is the, I'll take the next, RMS current and average current of diode D2. RMS and average current in D2. So the formula here ID2 RMS is equal to IS RMS is equal to square root of, note in the formula here, D by 3 into IS minimum square plus IS minimum into IS maximum plus IS max square. This is the formula here. So as you know, D is 0.5 divided by 3 into 14.25 square plus 14.25 into 15.75 plus 15.75 square. So this would be 10.61 amperes. So this is about the RMS current, right? Next, if I find out the average current, ID2 average or ID2 DC current. So D into average of this IS minimum plus IS maximum divided by 2. So D is 0.5, IS minimum is 14.25, IS maximum is 15.75 divided by 2. So you'll get 7.5 amperes. So this is one current flowing to the D2 here. Similarly, what is the RMS average currents in RMS and average current in D1? Okay, so if you want here, I'll just share where is the D1 and D2 circuits. Just a minute. So this is a circuit that we have discussed. So we are talking about, up to now we discussed about the D2 currents. Okay, current in this D2. Okay, now what is the current in the D1? Okay, so that we are want to discuss here. So average and RMS currents in D1. So ID1 is equal to square root of 1 minus D by 3 into IS minimum square plus IS minimum, IS maximum plus IS max square. So this is the formula. And if I substitute here 1 minus 0.5 divided by 3, so 14.25 square plus 14.25 into 15.75 plus 15.75 square. So we are going to get the answer is 10.61 amperes. So similarly, this is RMS current. So ID1 average, that is equal to 1 minus D times of IS minimum and plus IS maximum divided by 2. So 1 minus 0.5 into 14.725 plus 15.75 divided by 2, that is equal to 7.5 amperes. So this is the answer. Current flowing through D1. Okay. Now, what are the other currents here? So what is the magnetizing current? Okay. Peak value of magnetizing current, IM. So is you know that IM peak formula which we already discussed, D into V1 divided by Fs into Lm. So that is equal to 0.5 V1 is the input voltage divided by 100 into 10 power 3 into 2. Lm value we got is the problem it's given, right? What is that value? The problem you mentioned. Magnetizing inductance, yeah, 2. Mentioned is 2 millihenries. Yes. Okay. Now, yeah, solve for this answer. We are gonna get 0.5 amperes. Now, after this, we have to discuss about what is a reflected uh, currents or reflected secondary transistor current. Reflected secondary currents. Okay, so in this one also we are going to have a minimum currents and maximum currents. If we talk about secondary, so IS minimum, reflect means dash. Okay, IS minimum means reflected current, dash means reflected. It indicates so which is equal to n times of IS minimum. So reflected means we have to just multiply the turns ratio to uh, the secondary current. Okay, so reflected is always what is the effect in the primary can be reflected. Right. We have a reflected primary current that is equal to IP minimum, that is equal to uh, IS, that is equal to IS minimum dash, and whereas IP max is equal to IS max dash plus we have to add peak current, the magnetizing peak current also. Okay, that is equal to 1.71 amperes, and the secondary is the peak current we have to add, right? We have to add uh, the current here. Okay, so what is that current is? Yeah, so IS maximum current is so 1.89 plus magnetizing current is 1.5, 2.39 amperes. Now, what is the again what is the average and RMS current flowing through switch? Okay, average and RMS currents in switch Q. Okay, so current IQ, RMS, that is equal to primary current of IP RMS is equal to square root of D by 3 times of IP minimum square plus IP minimum into IP max plus IP max square. So that is equal to square root of 0.5 divided by 3, 1.71 square plus 1.71 into 2.39 and plus 2.39 square. That is equal to 1.456 amperes. So this is about the IQ RMS. So similarly, what is IQ average? IQ DC is equal to formula is D into IP minimum plus IP maximum divided by 2. So 0.5 into 1.71 plus 2.39 divided by 2. That is equal to 1.025 amperes. So this is about the current flowing through, average current flowing through the switch Q. And finally, so we'll also having a what is the current flowing through. So RMS and average currents in territory winding. Territory winding. Okay. So what is the IT RMS is equal to square root of D by 3 times of I magnetizing peak current. So it is 0.5 by 3 into 0.5. It is equal to 0.204 amperes. Next, I territory average current is equal to D times of, so initially it is 0 current, right? So maximum current is peak current, peak of magnetizing current divided by 2. It is equal to 0.5 into 0.5 by 2. That is equal to 0.125 amperes. Okay. So this is the answer here. So the problem, yes, I just want to revise here. The problem which is mentioned is, so what are the peak inductor output inductor value for the peak current ripple of 10%. Okay, that we have find and determine the various components of currents. Okay, so output inductor current is this much 40 microhenries. We got it, and then we have also find the various currents. We have find various currents in that. Okay, so this is the answer for that. Okay, similarly, so in this one we had only discussed about the various currents. Okay, now in this continuous conduction mode of forward converter here, what are the output voltages? What are the output voltages that we discussed now? Okay, so our next topic is uh, continuous conduction voltages. Continuous conduction voltages in forward converter. Up to now in the problem, we had only discussed the currents, various currents that we discussed. Okay. And what are the voltages here? Okay. Now we discuss about here in the switches, how many switches we have used. Single switch, right? So it is a single switch forward converters. So are relatively high voltage across various semiconductor devices. So we have used single switch here in the forward converter. So these are highly relative in voltages across various semiconductor devices. Like what are the various kind of semiconductor devices that we have here? We have a switch Q is there, diode is there, D1, D2 is there, okay, D3 are there. Okay, so they are relatively high voltage across various semiconductor devices. So if you remember here, we had 3 modes of operations here. Okay, so in the first mode, I'll just quickly revise here. The first mode, what we had, so in the first mode, the switches will be conducting at that time. The current flows in the primary and also D2 in the secondary is going to conduct, and thereby the current is flowing in the load. Now in the second mode, when the switch is off, Okay, secondary D2 will be off and primary D3 will be on, so that accordingly it will demagnetize it. Demagnetize the primary winding. But still there is a current is flowing in the secondary winding because of the inductor energy stored. And third case that we have discussed here, in the third case also, there is some current is flowing. Right. The third case also there is some current is flowing. Right. Here this is the thing here. In the first case, okay, in the first case we have turned on the Q, and in the time D2 will be on, current is flowing through the load. Okay, so that means the coil is going to be magnetized in this. And in the second case here, we have turned off here the switch off at the time, and the D3 will be turned on to demagnetize this primary coil. It is demagnetization process. In this demagnetization, when the switch is off, the D2 is also will be off. So when the D2 is off, the energy stored in the inductor is going to change their polarities to maintain the current in the same direction. Current I0 is also flowing. And in the third case here, we have turned off the switch. The D3 also off and D2 is also off. But still there is a current in the through the load because of the energy stored in the inductor through D1. Here also the D1 is conducting. And the first case D1 is off. Okay, so this is what the discussion that we had in the last class. Okay, now in this for these cases here, what is the voltage across inductor? Okay, if you look at this here, voltage across inductor from, so up for the D into TS case, this is the on switch here, and for the 1 minus D into TS, it is off state, and this will be continuously going in this operation here. And if you look at this here, the magnitude of this will be V1 and this will be V up here. So this will be voltage across inductor. So if you look at this, what is the voltage across inductor? This one. This voltage is N into the voltage across this one is N into V1 and output voltage is V1. I want the voltage across here. So this voltage minus this voltage, that is N into V1 minus V0 will be voltage across inductor. Okay. Now similarly, what is the primary voltage? What is the primary voltage? So if we talk about this is a primary. Okay. The primary voltage when it will be there. Okay. When the primary is going to conducting here and the time D into TS time, there is a primary voltage. Okay. And in the secondary side, now when the second mode of operation after this here, there is a because of this energy, there is also some continuously in the negative way here. And during the third like off case here, there is no point of energy in this case here. There is no question of the energy because there is no energy from up to this side and only the energy is flowing in the load side. So there is no conduction in this case. Okay. So I mean to say that here during the first mode of operation, the primary is conducting here. Second mode of operation is there is a demagnetization is taking place in this place, demagnetization up to this, and like you take not up to this case here. And in third case, there is no question of the conduction in the this place, no conduction. Okay. And if I talk about this switch voltage here, the VQ transistor voltages. So this is a switch that we have used. Okay. So during this 1 minus D into TS period, there's a increase in the transistor voltage peak here. And next here, up to 1 minus D times, there is again demagnetization. And the third stage here, there will be no conduction. So this will be keep on repeating. Now, what is the voltage across diode D1? Where is the D1 diode here? So this D1 diode. Okay, when primary, the Q is conducting into D into TS period, there is no current here. Okay, there is no switching of this. I mean, there's no diode is conducting. That means it will be open circuited. When the switch is open circuited, what is the voltage here? The negative voltage of this source here. This will be the negative voltage. Now in the second case here, in the 1 minus D times here, this case, it will be conducting. This will be a 0. Diode is conducting means current is flowing 0 and continuously up to this third year also there is no current here up to the third part. And the moment when it is coming to the first case again, negative voltage and continuously here. So this is the, I would say this is the first mode here. This is second and third mode operations. And when it is going to the here in this part again, the first mode is going to conduct. This is the voltage across diode D1. Okay. And similarly, if I discuss about the next one also, what are the different what is that modes? Okay, this is almost we discuss here. And next, so the voltage here. So if I talk about the voltages, so I'll discuss here. Right. Okay. Now, during these three modes of operation, the voltage, like VQ max, we call it as. So VQ max, we already discussed here it. And right. So as you know, the first case, it is going to be during the first mode of operation, it is going to be magnetized. In the second mode, it is going to be demagnetized, that we also discussed. And the reflected voltage of the territory. So reflected voltage, how we call this reflected voltages. So NP by N territory winding into V1. And so what is the maximum voltage across? What is the VQ max here? What is the maximum voltage across the switch? So that is equal to, we have found a V1 into 1 plus NP by NT into, so there is again initially there is a overshoot is there at voltage across the switch into overshoot. Okay, so this is the maximum voltage across the switch. Okay, and it is also required some uh, D-rate semiconductor device. Okay, so you know that semiconductor device. So there is a voltage switch withstanding capability is there. So if we apply the, if we manufacture the same amount of the voltage that we are going to operate, it cannot withstand. So we must have some safety operation voltages. So for that one, so we have to necessarily have a D-rate semiconductor device in order to D-rate semiconductor device in order to operate the device in a safely. Okay. So for this D-rate here, so we have to use 80% of the rated voltage, 80% of rated voltages. So for the duration here, we have to use 80% of the rated voltage. Like for the SIP, so VQ rated is equal to 80% of VQ. Sorry, this is a VQ max. Okay, so VQ max is equal to 80% of the VQ rated voltage. VQ max, the maximum voltage that we are going to be there across the switch is equal to, which is 80% of the rated voltage. Okay, so if we write it, what is a VQ rated value? So 1 by 80% means it's a 1.25 times into VQ maximum. So if you operate this voltages, or if you have this voltage of switches, so that it would be a easy operation and also safe operation. If you come to the switches here. Now, we also have a diodes is there that right here, right? We have a diode D1. Okay, so it is experiencing a highly, we can call it as relatively high voltage. The output voltage across the diode D1 here. So here, what is the maximum voltage across the diode? What is the maximum voltage across diode? So VD1, I'm talking about the diode D1. Diode D1 maximum is equal to N times of V1 plus VD1 times of peak overshoot. Overshoot voltage will be there, right? Overshoot voltage across D1. This is the overshoot voltage of D1. Okay, so this is the formula. Okay, now we will discuss a small problem on this. So a forward converter. So in the previously where that we discussed, right, we will take that problem example and we will have some parameters for that. So in previously we have find the currents, right? Now we will add the voltage here. Okay. Now determine the, so a forward converter that we discussed previously. So voltage range from 200 to 400 volts. Assume that peak overshoot voltage is 100 volts and 10 volts in the secondary side. Okay. The forward converter is in the previous example. Determine the maximum voltage seen by the devices and what are responsible voltage for semiconductor components. Okay. So that is he mentioned here. So first is mentioned that what is the maximum voltage seen by the devices. So what is the maximum voltage across the input side here? So VQ max. VQ max is equal to formula just now. What is that? This is V1 into 1 plus NP by NT plus VQ overshoot. The same formula here. So V1 into 1 plus NP by NT plus VQ overshoot. So input voltage is 400 is given, and so is the turns is 1 by same turns ratio, input and output plus 100. Peak overshoot is given as 100 here. So that is equal to 900 volts. Okay. Now this is the 900 volt is VQ max. Now where the maximum rated voltage of the device. Now next one is, so the is maximum completed, right? Minimum we have to take minimum rated voltage of device. So VQ rated. Just now we discussed here VQ rated is greater than or equal to 1.25 times of VQ max. VQ max. Okay. So 80% of the rated value means 1 by 80% will be 1.25 times. 1.25 times of VQ max is 900. That would be 11.25 volts. Okay. So approximately it could be taken around the value of 1200 volts. So we have to choose 1200 volts, a rounded value. It would be appropriate for the switch to when it is derated. Okay. So if you want to operate this voltage means we have to choose a device voltage of 1200 volts. Okay. Now, similarly, we have a secondary device. We have a diode is there, right? So secondary diode maximum voltage VD1 maximum is equal to N into V1 plus VD1 overshoot. So N is 1.12 into 400 input voltage plus overshoot voltage given as 10 right in the problem. So it is 58 volts. So minimum voltage of the diode, so VD rated is equal to, not equal to, it's greater than equal to 1.25 times of VD max. Okay, so I have taken the greater means, so whenever the device operating voltage must be greater than the operating voltage. So it is 1.25 times of 58. So this would be 72.5 volts. So approximately you can make it around of 80 volts. So 80 volts around 10 volts you have nearest value that you have to be chosen for the appropriate of diode when it's derated. When it's derated. Okay. So this is what the thing that we have. Okay. That is what the problems